Eun-jin Kim, who apparently has a very clear Korean name, nevertheless is connected to us from the UK. And let me tell a few words about Professor Kim's the CV, so to say. So she had finished her Bachelor of Science in Korea at Yonsei University in Seoul in 1990, and then moved on to finish a PhD in physics also at the University of Chicago in the United States. And from then on, she moved quite a bit in between the United States and the United Kingdom. So being first working as a, let's see, as a postdoc at the University of Leeds in Exeter, then moving to Boulder, Colorado, then to University of California in San Diego. And then she moved to a position at the University of Sheffield, where she stayed for quite some time. And then she moved, I think this is quite recent, 2 years ago, for a full professor position at the Coventry University in the Fluid and Complex System Research Center. And that's, I guess, from where she is right now connected to us, well, at least affiliation-wise, because it's quite early. Again, we are very sorry, but apparently this is not a problem with our speaker, who is an early bird, because it's quite early still back in the UK. So today we will listen to, it looks like a very broadly placed talk on information theoretical method for understanding complex systems. So we are very interested to see the details of that. So Professor Eun-jin Kim, please start with your presentation.
Yeah, thank you very much, and thank you for the nice introduction, and also for this invitation. I'm very happy to have this opportunity to meet you and to have the opportunity to present my work. I have been thinking about this problem for 5 years now. For me, it is something that I think about every day when I get up, when I go to bed. But it may be something that is not really so familiar to you. So if you have any question during my talk, please feel free to stop me anytime. And that way I will feel better, because I don't want to give you a talk which doesn't make any sense. I want to have a little conversation over something that we share the same common interest. So please do stop me and ask me any question. So here is the next slide. Why doesn't it go to next slide?
Sorry, Prof. Kim, maybe you just need to click on the slide with the mouse, and then you could probably.
Oh, yeah, I need to scroll down. Yeah, thank you. So the outline of my talk, I will give you a little motivation. And okay, here is blocking my screen. So let me just rearrange the, yeah. Okay, so I will start with the motivation and introduce information geometry, in particular information length. Then I will show how this can help us understanding attractors of dynamic system by going over a few examples listed here. And then I will talk about the geodesic and how we can use this geodesic for optimal control. Right? Some examples of complex system. I mean, my background originally was from the astrophysics, and then I got interested in the fusion plasma, and then I got interested in biological system, and now I'm getting more interested in the small system, quantum system. So I have gone through many different fields. So look at the beautiful universe. And that's example of complex system. And then you also have the Earth, and people are talking about organization of the Earth's environment and how this CO2 emission can be controlled. And we have this human brain, which is maybe most complicated, complex system. And there are many different types of the network, like a cellular network, biological network, or the even social network. And we can even find the example in the unemployment rate versus the stock market behavior. And what is involved in different complex system is very different. And obviously they work on different lengths and time scale and look very different. However, they share similar information processing. And this was in fact noted by Gelman in his statement that I have written here. So I will give you 1 minute to read what he said. Okay, so I hope you have read it. And why do you care about common feature? To me, at least, identifying common feature is fun. Also, it enables us to use the knowledge about one complex system to understand other complex system. It means it's very economical. And I have been keen on exploring information geometry as such a common feature. I wanted to know how we compare different dynamical systems and how we characterize attractors, for instance, stable or chaotic equilibrium, and how force affects the geometry around the equilibrium. And the information geometry applies the concept of the geometry to the probability and statistics. And the crucial feature of the complex system is the dynamics. And they are changing with the time, they are evolving in time. We can use information geometry to assign distance or geometry to this time evolving dynamics. And that's why I have been interested in, because I realized that time evolution is quite important for understanding complex system. To understand what I mean by this is easier to start with a simpler question as to how we define distance between two PDF. And when you say PDF, the usual example is Gaussian, is the usual victim, because it's simple. It's determined by the two parameters, say the mean value mu and standard deviation sigma. Mean value also represent the position of the PDF peak here, and standard deviation gives us the measure of the width, how wide the PDF is. For notational convenience, we also use inverse temperature beta, which is 1/2 sigma square, and sigma square we also call variance. Is this all okay? All right.
Yes.
So now I have 4 different Gaussian PDF, and they look different. And technically, because it's a Gaussian PDF, they are different because either they have a different mean value or different standard deviation. And we are all scientists. We want to be more quantitative. We want to have some quantitative measure of difference. And I'm going to quantify the similarity or disparity between any PDF by using number or dimensionless distance, such that this distance is exactly 0 if you give me 2 identical PDF, and distance increases as PDF are more different. And to do this, it's useful to consider the parameter space or statistical space using the 2 parameters of the Gaussian PDF, mean value and standard deviation, as 2 axes. Here I'm using the mean value as x-axis and standard deviation as y-axis. So consider 2 PDF A and B, which have the same width, but the mean positions is different. So A and B will have the same y coordinate because they have the same width and different x coordinate. Okay. And now let us consider another pair of Gaussian PDF C and D, which have the same width, therefore they have the same y coordinate, but but then C and D are wider than A and B. Therefore, the separation, and therefore the y coordinate of C and D is larger than y coordinate of A and B. So we can mark these 4 Gaussian PDF in this statistical space. And then if you look at A and B, C, D, and it looks as if the distance between A and B is shorter than distance between C and D. Okay, and that is correct if the geometry is flat. However, if you calculate infinitesimal line element dl square in this statistical space, it involves the metric tensor Gij, which is given by the Fisher information metric tensor. And Gij is not constant, but involves the standard deviation in the denominator. That means that the wider PDF, effectively the shorter the distance. And since C and D have wider width, effectively the distance C and D is smaller. So that we can have a situation where distance between A and B is equal to distance between C and D. Okay.
I have a question. What are the assumptions which we have to make in order to come up with such a distance definition?
We are using the Fisher information metric.
Well, I mean, what do I have? Well, yes, but I don't know this. So great. Now I know how it looks like. But what are the assumptions which I have to make in order to come up with such a definition of such a distance?
We are going to, I mean, this is the 2 parameters, mu and sigma, which fix the PDF. So what we want to know is how PDF depends on 2 parameters.
Right, but
so
I may come up with my own definition of a distance. And so what?
Yeah, of course, yes.
What goes?
Yes,
so that my question was, what goes into this Fisher information distance as an assumption in order to come up with the Gij which you wrote there?
I mean, I'm using an example of the distance. Of course, there are many different the metric that you can consider, and using, I mean, for instance, Weissman metric, all sorts of different metric tensor. But I'm using Fisher information as an example. For me, it captures the nice property that for the Gaussian PDF, the width of Gaussian PDF gives you the uncertainty in measuring the mean position. It gives accuracy. It's the smallest length scale that you can really resolve using the PDF. So to me, it's very intuitive. So I wanted to use the concept to push my theory through.
Thank you.
Sorry, one other quick question, Prof. Kim. So just wondering, here you have a Gaussian which is parameterized by 2 parameters, but what if you have a more general PDF? Could this idea of Fisher information be generalized further?
Yes, I mean, if you have the complete set of the parameter that determines your PDF, you can do it. But so, in reality, if you have like some unknown statistical process, like, I mean, there are many data, and it's very difficult to what parameters determines that stochastic process. So this is a particular case where you have full control of your parameter that determines the dynamics of your stochastic system. But
I see.
it's
Sorry, so you're assuming that a Gaussian evolves to Gaussians always. It's not that a Gaussian is going to some other state, basically, throughout your stochastic process.
Yes, I think at the beginning of my talk, I try to stick to Gaussian because the property is very simple. As long, I mean, if you give me mean value and the standard deviation, I know the PDF is Gaussian. But the more complicated case is, of course, I mean, the property of complex system is not Gaussian. That's the interesting bit. It's hardly Gaussian if you look at the complex system.
Yeah.
So I'm moving on to the topic. But this is just to give you idea about what this distance means in that I'm talking about.
I see.
So the bottom line that I want to bring up here is that when you talk about distance, you have some sort of a ruler in mind. Yeah.
So it's
So
a standard Euclidean distance. No.
No, I don't think so. I think what we learn here is that we have to find a guiding principle to define the distance. That could be something, and so there's this visual information distance which we see here, but it's not exactly not just a ruler. So this is, I think, what Professor Kim was telling us.
I see.
There, Ihor has another question. We have another question, Professor Kim. So Ihor, please unmute yourself.
Yes, hello. So I just wanted to clarify, is it required that both probability distributions are from the same class, like Gaussian, or just that they have the same support in this statistical space, so the same number of parameters?
Yeah, for this simple exercise, I'm just considering a simple Gaussian PDF determined by the two parameters.
But is it possible with the same method to calculate the distance between two arbitrary probability distributions, both having two parameters determining them?
Oh, yes. I mean, yes. I mean, you can define your metric tensor using the Fisher information if you have a PDF that is completely determined by two two parameters using the Fisher information metric tensor. Of course, the form of the metric tensor will be different for different PDF. It takes this particular.
Sorry. So if it's not just one P, but P1 dependent on two parameters and P2 dependent on two parameters, you can still define this Fisher distance between them.
If they have different parameter dependence, it's not that straightforward. So if you have different parameter determining different PDF, I mean, it's not clear how you do this.
I see. So it's a distance only between two elements of a class of identically parameterized distributions.
Right. Yeah,
Thank
the
you.
same class of the PDF. Oh, this is brilliant. Okay, any more questions?
I think we can continue. Ihor,
Okay.
please
Right.
lower your hand, and yeah, I think we can continue.
Right, that's great. So here is some specific example how this concept is used. I mean, just sticking to the class of the Gaussian PDF determined by the mean and the variance, okay? And we are going to now calculate the actual distance that I'm talking about. On the left, we have two PDF with the same width sigma, and the mean position is different by the sigma. And what we do to calculate this dimensionless distance is to divide the difference in mean value, which is sigma, by the width, which is sigma. So we get about 1 unit difference. All right. On the right, we have now the 10 PDF, and they all have the same standard deviation sigma, and the difference in the mean value between the nearby two PDF is a sigma. So as you move from to the left to the right, so you fix the left to PDF, and you are going to compute the distance between the next or the second next. And as you move, then you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 9 sigma between the first and the last. So the distance will be 9 sigma divided by sigma, getting 9 unit difference. All right, and this is the simple case because all PDF have the same width sigma. And now, in general, when you compare two PDF, it's not necessary that two PDF have the same width. So here is the extreme case where two PDF have different widths but the same mean value. Say one PDF has standard deviation sigma and the other has 2 sigma. In this case, roughly we can imagine fitting two of the narrow PDF under one wide PDF. And this gives us approximately 1 unit difference. You can calculate exactly to show this distance is 0.9 something, is close to 1. But I'm just trying to give you some idea how this dimensionless number works. All right. So as you noted already a few times, the Gaussian is not necessarily, the PDF is not necessarily Gaussian. Furthermore, so far we didn't care where the PDF came from. We just considered some class of Gaussian PDF determined by the mean and the standard deviation. Now we need to look at more realistic case where the PDF comes from some time-dependent stochastic processes, say the stochastic variable x, and time-dependent probability density function is px at time t. One way of dealing with this case is to consider relative entropy or KL divergence between two nearby PDFs, say P1 at time T1 and P2 at time T2. And
Prof.
we are
Kim,
going to take...
sorry to interrupt you. We have a question from Igor again. Please
Yes.
go ahead and unmute yourself.
Thank you. I just wanted to continue a bit with the previous question of mine because it's not super clear. So it seems that in this way, this distance between two probability distributions becomes not just a characteristic of these two distributions, but it depends on the way the parameterization is introduced. Because I'm pretty sure I can just take two Gaussian distributions and just then introduce a new parameterization such that two specific Gaussian distributions will be the same, but in between the parameterization will be completely different. And it seems that then I will get a different distance for the same two distributions. Is it so? So is it Fisher information distance information metric parameterization dependent? Yeah,
it is. I mean, of course, the two coordinate system in this statistical space is set by the parameter. So if you use different parameter, then you will have a different metric tensor that defines the distance in this statistical space. But what I'm going to show you now is that there is something that is invariant under the coordinate transformation, and it doesn't really require knowing what the parameter is of your system is. And it also, yeah, and you can also apply this for any PDF. It doesn't need to be Gaussian. All right.
Thank you.
And the Fisher information as well as entropy has this problem that when you change the coordinate, if you do the coordinate transformation, the absolute value of the Fisher information or the entropy changes. So there is a slight difficulty with those concepts, although it's very useful. So the one that I'm going to introduce called information length is invariant under those transformation. And it doesn't need to have the complete knowledge about what parameter you are using. Actually, we use this concept to understand how the music evolves in time. You tell me, you listen to Beethoven, what are the parameters that determines the Beethoven music? And you listen to Mozart, and what is the parameter that determines that the music signal? So we can still apply this method regardless of our ignorance about the parameter that determine the dynamics or the shape of the PDF. All right. So continuing this exercise, we are going to consider relative entropy between P1 and P2. And we are going to look into limit where the time difference between T2 and T1 becomes 0. So we are considering the infinitesimal relative entropy. And we take the limit where dt approaches 0. Then you can rewrite this the infinitesimal relative entropy using the Taylor expansion and also using the total probability conservation in this form. And so dt, this is to the leading order dt. So there will be the dt to the power 3 and the 4th, but since we are taking the small dt limit, I ignore all higher power. Okay. And here dt obviously is the time difference, so dimension is time. And tau here is given by this form. And we can show that the tau has the unit of time. So what we have on the right-hand side has no dimension. Okay, so you can introduce infinitesimal dimensionless number, say L, and that square gives us this dimensionless number. Alternatively, you can write the rate of change of L in time gives you 1/tau. This tau is the time scale of the information change, and that is due to the probability density function changes with the time. And I understand that this tau was also shown to be linked to the smallest time scale of dynamic fluctuation and also speed limit, and presented in this paper. And one of the co-authors of this paper, I understood that presented a talk at this seminar series a few weeks ago, unless I read it wrong. Okay, so I'm going to call this dimensionless number L the information length. And that is obtained by integrating the 1/tau. And physically, that is obtained by measuring the total clock time from 0 to t in unit of this character's time scale of tau. So as long as you know how the PDF changes with the time, you can always calculate this distance. You don't care about what the parameters that are controlling the PDF, or whether PDF is Gaussian or something else. Okay, as long as you have well-defined integration integral that you can perform. And physically, this information length gives us the total dimensionless number of statistical state that the system passes through, starting from the initial distribution at t equals 0 to time t. Okay? And obviously, if you look at the definition of tau, that involves the magnitude of something else, so it is non-negative. So when you integrate one over non-negative value, the integral LT cannot be decreasing with the time. Okay, so LT is a non-decreasing function of time. And we can show that both the character's timescale tau and LT are invariant on the nonlinear coordinate transformation. And if you introduce time-dependent coordinate transformation, it's a different story. But as long as your coordinate transformation is independent of time, these two quantities are invariant. So it's very useful quantity, and physically it means that the number of statistical state the system pass through doesn't depend on what coordinate system that you are using, and that makes sense. All right, and it's uniquely defined as a function of time if you fix your initial condition and parameters. And it's useful to understand the dynamic systems such as attractor and force geometry link. And hysteresis, for instance, in phase transition and the correlation. And for the rest of this talk, I will focus on the attractors and force geometry link.
Igor, do you have
we have a...
Oh, yeah.
I just want to clarify, not very clear. What are statistical states here? Are there different realizations of X?
So if you I mean, I make this analogy quite often. Now let us assume that you have the oscillator, okay? It's an oscillator with a period 1 second. And if you have the 5 seconds, with the 5 seconds, you have 5 oscillation, okay? So this one oscillation is some sort of one statistical space in very crude sense. Okay, so here the analogy here is if the tau is constant, that means the tau gives you how rapidly information changes, information content changes in your system. So we are now counting how many different statistical states that the system evolved through by measuring how many of by measuring the total clock time in unit of tau. So if your system changes every 1 second, it's not oscillation, but somehow the PDF changes such that it changes information content by 1 second. And if this tau happen to be constant, within 5 seconds, you will have 5 changes in the statistical state. Okay. So in general, I mean, I'm going to talk about the relaxation problem where the tau is not a constant. So we are measuring how the infinitesimal time element is seen in unit of this character's time scale of tau. So for PDF like PXT, if this PDF is Gaussian, happen to be this change in the PDF can be due to PDF moving or PDF getting broadening or narrowing or the combination of the both. So here the beauty is that we are not really trying to find out what exactly happened to PDF to give us one different statistical state, but we are looking at overall change. I mean, you use this entropy concept very well. I mean, it's a beautiful concept, but what I'm not happy about entropy is that you have a PDF, say, centered around x equals 0. You calculate PDF, the entropy, and you move your PDF at some other place, keeping the width the same, then you get the same entropy. To me, these two PDF are different because in complex system, there is overall change in the mean value on top of the variance. So if you only naively look at the difference in the entropy, you get 0, no matter whether PDF has moved or not. So using this concept, we also proud not only the change in the width, but also in overall shifting and also the change in the shape. The Gaussian PDF may become quartic exponential or something else. So this tau gives you the overall change that is happening to your PDF. So your question is very good, but it's not easy to answer your question exactly what gives you one statistical state difference. There will be different scenarios that give you that one statistical state change.
I honestly still very confused because I still don't even vaguely understand what is statistical state. So there is a time, there is some space of x of random variables, and there is some probability distribution. So even like qualitatively, how can I understand what is a statistical state in this case?
Okay, so if you forgive me, I want to go back to my simple example of Gaussian PDF. So this gives you one different statistical state. You have a PDF with the same width, sigma, and if two PDF happen to have the mean value different by the same sigma, when this red PDF becomes blue PDF, you have one statistical state changing.
So it's okay. Maybe then it's the number of statistical states.
Igor,
Yes.
I suggest we maybe let the speaker continue and see where it brings us. I think right now we can take it that the statistical state is a given PDF realization. That's it. Now, but I think Igor is asking about probably more applied examples and so on. So let's see where we go, Igor. Fine, and keep your questions, and maybe we'll see whether some of them can be resolved. Thank you.
All right. Yeah, that's great. All right. So Now, please stop me again here if you are not familiar with this topic. I mean, I can do this thing now in my sleep. I did a million times. So what do I mean by attractor? If we start with a simple linear process called OU process, it's a driven and dissipative system. So it's driven by short correlated Gaussian noise psi. And it's useful to push the analysis to assume that psi has a short correlation, so delta correlated, and has some amplitude d. And I'm using the angular bracket to denote the average over this, the stochastic noise. And X now damps linearly with the damping constant gamma. And it's driven and dissipative system, therefore it's a relaxation problem. If you start with some initial condition, this system wants to reach the equilibrium distribution. Okay, and I'm going to denote the X as a sum of the mean value X and then fluctuation delta X. And for simplicity, we are going to use the initial distribution happen to be Gaussian. And using the Gaussian stochastic noise, we then know that the probability density function for X is always Gaussian. And here you go, then if you determine the two parameters, the mean value X and then standard deviation or inverse temperature or the variance, then you are all set. We have a complete knowledge of probability density function for all time. Okay, mean value obviously decays from initial value exponentially at the rate of this damping constant gamma. And while the fluctuation amplitude delta x squared, which is 1/2 beta t, has two parts. One is due to the initial fluctuation delta x at t equals 0, which decreases with the time. So any initial condition will disappear because of the damping relaxation problem. But stochastic noise here, the psi will keep pushing the system. So it will give you some constant source of the fluctuation. Okay, in the long time limit, this goes away. So your variance will approach constant value, which is d over gamma. And in the long time limit, the PDF approaches the stationary distribution determined by mean value 0 and this variance. Therefore, PDF doesn't change any longer, and therefore the rate of change of information is infinite. It doesn't change it, so you need to wait infinite time for any change to occur. That is to say that there is no change in the information length, so the rate of change is 0. So alternatively, you can say that LT increases from 0 because your PDF now is trying to relax to the equilibrium, but then it approaches constant value in the long time limit. So we call this asymptotic value in the long time limit L infinite. And this L infinite gives you total number of different statistical space in reaching the final equilibrium starting from the initial PDF X0. And this obviously depends on the two parameters of your distribution, which is the mean value of X and or the variance. Alternatively, it depends on the initial mean value of X, X0, and initial fluctuation of X. So we are going to fix the fluctuation, initial fluctuation to be some constant, and we are going to look how this L infinite depends on the position of the initial Gaussian PDF. Okay. And we are going to consider the two processes, and one is the linear process that I just talked about, OU process. But I want to compare the effect of different force, especially nonlinear force, how this force affects the geometry around equilibrium. So I'm going to also consider the force, which is now given by cubic force. So it damps more quickly for larger X.
Sorry, Prof. Kim, a quick question here. The whole idea of this information length was based on Gaussian states, but now when you consider cubic force.
No. So Gaussian was introduced to give you some idea about how this statistical state work. But the definition that I introduced was general. I didn't, when I calculate this infinitesimal relative entropy, I didn't care about the form of a PDF.
I see.
It only involves the rate of change of PDF. Okay.
Okay.
So it
Thank you.
works for, thank you. Okay. So now both process gives you the relaxation and driven problem, and it's, they in the long time limit, both process will reach equilibrium, and this equilibrium distribution is centered around x equals 0. For linear process, is Gaussian distribution, as I talked before, it's Gaussian distribution, and for cubic process is quartic exponential. It has a stronger dependence on x to the power 4. And we are assuming the psi also, again, has the amplitude d. And I was curious about this question in the first place because once you talk about stochastic process, there is no meaning of a point. When you say point, it's all respect to the probability. I mean, if you want to talk about point, it's really delta distribution. So what I was interested in is if you were to choose any point in x coordinates, say x equals y0, how close is this point to the equilibrium point? Okay, an equilibrium point is not really a point because you have equilibrium distribution around the equilibrium point. So I want to know how close any point in x to the final equilibrium. And I measure this distance by using the total information length. So what I do is I put a lot of points around specific point at x equals y0 to make a narrow PDF and let it evolve in time. And as it evolves, it will move to the left, and then you will adjust the width to match the final equilibrium. And then when you reach the equilibrium, you will have the unique L infinite. Okay, you have a number, which is asymptotic value of the total information length in the long time limit. Okay? So you get a number, L total, for one initial condition for y0, and then I try different initial condition by choosing different y0. And I try a bunch of them, and I want to look at how this L infinite depends on y0. Can you take a guess? If you look at this scale, it's linear, yeah? These points are linearly spaced. So would you expect linear relation? Okay, let me show you the answer here. Actually, it's linear for the linear process. All right. And now I wanted to see how different force, like the cubic force, affects the results. So I did the same exercise. You start with some narrow PDF around x equals y0 and let it evolve until it reaches equilibrium, the quartic exponential. And then I try different initial conditions. I do a bunch of them. And I plot the L total against the y0. And in the case, you do not get linear line. Although if you look at this coordinate, it looks linear in x coordinate, but it's not linear. You get some sort of a blue curve. So if you plot the blue curve in using log and log scale, you can identify range where the L infinite actually has the Pauli dependence on y0. And this Pauli index P happened to be between 1.5 or 1.9. I can push in my analysis to show that it has a lower limit 1.5 and upper limit 2, but I couldn't really get this value. But this value was obtained numerically because it's difficult to get exact PDF for the cubic process.
May I just interrupt shortly? Just to clarify, what is plotted on the y-axis? On the x-axis, we see y.
The mean value,
right?
yeah,
Right.
initial mean value.
And what do we see on the y-axis?
It's L total, is the L infinite, which is the total information change that occurs when the initial PDF reaches the final PDF. So this is relaxation problem. So if you start with the initial PDF, you will try to move to the left and PDF will change.
Right.
And then L information length will increase. I mean, information length is 0 to start with, and then it will increase. And then it will approach a constant value in the long time limit because PDF does not change anymore over
Right,
time.
but the plot doesn't look like that. Can you show the next slide, please? Right, so what I see, you say linear process. So where do we move? Let's take this red dashed line. So how do we move along it as time goes on?
No, this one is very expensive.
Expensive.
No, I did not include a figure showing how the LT changes with the time. I can just draw a rough sketch. I mean, it will increase like so, and then it will asymptotic to some L infinite constant value. So you try a whole one time, you try one PDF until it reaches equilibrium and you get A value. So you get 1 point here.
Well, I still don't get it. So you start at the time t, at your initial time, you start with a distribution which has a non-zero y naught. So this is right, or x actually, or whatever. Yeah, so
Equal y0.
yeah, first moment which is non-zero, I guess, right? And then you move, and then you let well, then you evolve, so to say, your distribution according to your stochastic differential equations, and then y0 should, or whatever you call this, it should become smaller. So in your next slide, you should move to the left and not to the right. I just don't understand that.
No, y0 by definition is the initial mean value.
Right, okay.
Okay, and the mean value of x will decrease with the time and will become 0 in the long time limit. So what I'm plotting is plotting against the initial mean value y0.
So what is the meaning then of that plot on the next slide? You plot,
so
you change simply your initial distribution, and therefore what?
So what what next slide means is there is a linear relation. So for instance, now I have y0 here 0.7. Yeah.
Oh, I got it. I think I got it. So the bigger y0, the bigger process. Yeah.
And then you will get like L infinite, which is I don't know what it is here. If I look at 0.7, it's about 2,000. Roughly say it's 2,000. Okay. But what I'm saying by linear relation is that now if you choose a PDF, initial PDF with y0 value half of the 0.7, which is 0.35, which is around here, then the L infinite, which is a total number of different statistical states that the system needs to go through, gets half. Becomes half.
Right, yeah. And that's different for the cubic force.
Right. So for the cubic process, although if you move this position y0 to the half, like 0.35, the total number of states that occurs is not changing by half. It's changing with some power law.
Sure. Thank you.
So although if you naively look at x coordinate, it looks linear, but actually because the force, I did some calculation of a time-dependent PDF, and I realized that if you have a cubic force, actually there is a link between time and coordinate. So time and coordinate becomes very confused. So that gives you this curved structure around the equilibrium. But my co-author didn't agree. So and we have this power law scaling, and what's more interesting is that we get always this straight line for the linear process, no matter what d you use or what initial variance you use. But for the cubic process, now if you use different stochastic noise d strengths or different initial fluctuation, then actually power law also changes. So the P now is not constant. It depends on the parameters. So to me, it was some sort of multifractal, and the referee did not like the terminology. So I was forced to remove the terminology.
Thank you.
Right, so that was looking at the 1D system where you have one stochastic variable. How we now generalize this to the higher dimensions, for instance, 2D. And the simple example that we can consider is the Kramer equation for the two variable x and v. And the rate of change of x is just velocity, and now v is driven by stochastic noise psi, and it also undergoes some linear damping gamma, and this system has natural frequency omega. Okay, so it's oscillatory damped and driven system, and it's a linear process. And if you use Gaussian noise and use initial Gaussian distribution, the PDF all time remain Gaussian. And this Gaussian PDF is completely determined by the mean value of x and v and the covariance matrix. And we can show that in the long time limit, the mean x value and mean v value becomes 0 because of this damping process. And the covariance matrix approaches constant value. So we calculate the exact time dependent for any arbitrary Gaussian PDF. And then we did a lot of cranking to express information length in some form. And in the end, we had to use a numerical integrator to perform the integral and time integration. And here, note that now we are dealing with the two variable x and v, so integral involves both x and v. And obviously now to look at the geometry around the equilibrium point is x equals v equals 0. So we can either fix the x0 to be 0 and then scan over v0, or vice versa. And L infinite also depends on initial fluctuation in x and v. So we are going to fix initial variance in x and v and explore how the L infinite depends on initial x0 and v0 around equilibrium. And what I was interested in is the effect of two time scales now. And previously we had only damping constant gamma in addition to dissipation due to dt. But now we have two characters time scale. One is due to the dissipation gamma, and the other is this natural frequency. And in this system, there is something called the critical damping. When gamma equals to omega, then oscillations start disappearing. So I wanted to know whether this information lengths pick up some of the physics due to this critical damping.
Prof. Kim, we have a question.
Yes.
Hi. May I ask, first it's a trivial one. This is in the formula, this L italic, it's just your information length L, or it's something different?
Yes.
It's the
No,
same.
this is information length LT.
Yeah, so it's exactly the same as one line below. Yes, this is L.
Yeah, that's the same. But now here you have two variable x and v. Our PDF actually is a joint PDF. So the integral is actually multiple integration. It's just a vector here. It's a boldface. So it's a dx dv.
Ah, okay. This is exactly the point. So you mean that you're taking integral in both variables, and x and v.
That's right. Yeah.
Yeah, and then the question is, if you are saying that they are both Gaussian, and at large time the mean value tends to 0. So
that's right. So I'm going to now look at how it depends on the initial mean value. Yes, in the long time limit is 0.
Okay.
So I'm going to look at how this L infinite depends on the initial mean value of x.
Okay, so actually you could write dx dv. Yeah, it's just a double integral on both variables.
Yeah, that's right. Yeah, this is double integral. Yes.
Okay, and this p is exactly the p above, which depends on both x and v. Okay?
That's right. Yeah. Yeah. It is pxvt. Yes. Thank you.
Okay.
And speaking of that, actually, once you go into higher dimension, you can also define the different information lengths. I mean, you can take the marginal PDF of x and then treat as a 1D system and calculate information length. And then you can take the marginal PDF of p, PDF of velocity, and then calculate the information length from there. But for this exercise, we just took the joint PDF and explore essentially how the L infinite changes in the plane. And the axis of the plane is given by initial x value and the initial v value. Okay, because we have two dimension that we need to scan over. So to simplify, I'm going to take a cut where the V mean value is 0, initial mean value is 0, and the other cut where the X mean value, initial mean value is 0. Okay. Yeah, once you go into higher dimension, our head spins. All right. So here is what we did. On the left, we fix initial V value, mean value to be 0, and we only scan over initial X mean X value. Okay. And we see bunch of straight line, and different line are due to different damping constant. And for this exercise, we fix the natural frequency to be 1. Okay. And if you have a good eyesight, you may realize there is some red bit underneath. Do you see it? On the bottom. And this red curve is actually for the critical damping when gamma is 2 omega. So that suggests at the critical damping, your information lengths tend to be minimum. All right? And on the right, we fix the initial X0 to be 0 and then scan over initial the mean initial mean V0. And you see another bunch of straight line for different gamma value. And again, you see the red line for the critical damping. Okay, so we are very convinced that even in 2D, we have this linear relation around the equilibrium point because linear process is Gaussian, and Gaussian process preserve the linearity of your system. Okay, the next exercise now look at how this information length depends on omega for fixed gamma, or how it depends on gamma for a fixed omega. And we use some initial distribution, which doesn't really matter for this exercise. So, and then we denote the critical damping by the dashed vertical line. And here you see it, and you see around the critical damping, you see the distinct minimum in the information length. And similarly here, you see the minimum of information length around the critical damping. For me, it was an entertaining exercise because I'm always care about how many different timescales are involved in any dynamics. And what this shows is that when 2 timescales associated with the gamma and omega becomes just 1 because there is no oscillation anymore, then your system somehow becomes simpler. And that is somehow information content is reduced and there is less change in information. And now you can reverse this argument saying that if there are many different timescales in your system, effectively they increases the information in your system. So they will increase the information length. But that's all about the stable equilibrium, where the PDF, no matter where you start initially, try to approach some nice stable equilibrium. And now we want to contrast this case with the chaotic attractor. And if you talk about attractor, the chaotic attractor, what comes to mind first is the logist map. It's a mapping, simple mapping that Feigenbaum did a long time ago with his pocket calculator. It's a simple mapping using the rule how we are going to update the X value at iteration t plus 1 from the previous value at iteration t. It's a discrete dynamical system. And here X is defined between -1 and 1. And A is the parameter that control the stability of the system. And as A increases from small value, it goes through the period of doubling. And when A is sufficiently large as 2, then system becomes chaotic. That means that no matter what initial condition you start with, if you wait long enough, you always evolve to chaotic attractor, which is called invariant density. And I have shown the cartoon figure for the invariant density, and you start with a narrow PDF at t equals 0, centered around x equals 0, 0.7. And after dozens of iterations, already this distribution evolves to this invariant density. Okay? The question is that if you were to choose any point, say x equal x0, how close is this point to your chaotic attractor? So to answer this question at t equals 0, as we did before, we put a lot of points to make narrow PDF around x equal x0. And then just let it evolve. This is mapping, so you can just use a simple MATLAB and wait long enough until it doesn't change anymore. And then calculate the total information length when you reach the invariant density. And then you choose different initial PDF and then repeat the same exercise. Okay. And we tried, I think, about 10 to the 4th or 10 to the 5 different initial distribution. And we plot how the L total depends on the initial X value in this figure. So what strikes us is that it's very spiky. Previously, we saw that information length monotonically increases from the equilibrium, but now if you were to change your initial condition by a little bit, then you have overall change in the total information length. So that is because the chaotic system has a sensitive dependence on the initial condition, and the sensitive dependence is similar to the Lyapunov exponent, meaning that the small infinitesimal line element undergoes exponential divergence because of sensitive chaotic dynamics. Furthermore, you can see several red circles which mark the local minimum in the L total. And in particular, the x equals 0.5, which is most unstable point, have the smallest total information length. That means most unstable point is most similar to the chaotic attractor. So unstable point, stable point is close, is most similar to the equilibrium, but for the chaotic attractor, because attractor is chaotic, the most unstable point is most similar to this chaotic attractor. So this L total versus the mean X value, initial mean X value also reveals the structure of your chaotic attractor and also the location of your unstable point. Okay, I cannot see the clock. Would you be able to tell me how much time I have now?
Well, we are a bit advanced already in time. What do you think? Would you make it in another 5 to 10 minutes?
Okay, I will try to go over the idea of geodesic. I mean, I may not explain everything, but I just want to give you some idea as to why I care about this problem. So on the surface of the Earth, geodesic is a particular point, a particular path with the shortest distance between 2 points. And in the statistical space, we can use a similar concept to define a path with the smallest information change, which minimize information length. And we can show that along geodesic, the rate of change of information is, or the character time scale of tau is constant. The question I'm interested in is how we find a geodesic for a given initial PDF, say at t equals 0, and final PDF at some later time TF. Okay, so I fixed initial PDF and final PDF. I wanted to find the evolution path that minimized information length. So here's a cartoon fit picture to show what I'm talking about. So say initially I have the red PDF, and at some later time I have a final PDF shown in blue. Okay, the question is how I'm going to move the PDF from right to the left to reach final equilibrium at later time. And for simplicity, I'm going to assume that both initial and final PDF have the same width. Okay. And how many different ways are there? Any idea? 1, 2, 3? Actually, there are infinite number of different ways of doing this. And 2 examples are shown in the bottom figure. On the left, the initial PDF is starting from initial PDF. PDF just moves at constant rate from right to the left without changing its width. Okay, it maintains the same width, but just keeps moving to the left. On the right, when initial PDF broadens first and then gets narrow before reaching the final PDF. And I'm going to show shortly that geodesic is more like this second scenario. And why do I care about such a problem? This kind of problem appears, for instance, in biology, when you have a large size tumor and you want to reduce to smaller size. And there is a measure of the variance for the tumor cell, and it represents the heterogeneity of your tumor cell. And there are ways of manipulating this width of this heterogeneity in tumor cell by using the gene reprogramming. So this problem can happen in practice when you want to reduce the large size tumor by killing it by radiation therapy or something else. And in the meantime, you can apply this gene therapy to control the heterogeneity of your tumor population. Okay, so I found the geodesic solution in the stochastic logistic equation for variable u. So u is non-negative variable, and it grows due to the growth rate gamma, and it has the nonlinear effect which saturates the growth due to crowding effect or the competition for the food. And I include some stochastic noise in the nonlinear feedback effect, and also some killing effect, the nonlinear killing that is proportional to u squared. Although the equation as it is nonlinear for u, you can use the coordinate transformation letting x be 1 over u and transform this to the linear equation for x. And obviously, if you shift your x coordinate by minus g gamma, it recovers all your process. So if the stochastic noise d and g are constant, and if you start with the initial Gaussian PDF, you know that you have the Gaussian PDF and it's all your process. There is no chance of finding geodesic solution. It's a relaxation problem. So what I did was now make D and G time dependent. And by finding geodesic solution, essentially I want to find how D and G should depend on time. Right? So information length is invariant on the time independent coordinate transformation. So I can consider geodesic using the PDF of X instead of a PDF of U. And I know that for initial Gaussian PDF, my PDF is always Gaussian, which is some function of dt and gt. And I can calculate the mean value of X, which I call yt, and the inverse temperature beta t. And then I know that for Gaussian PDF, the information length involves this combination. And I'm going to minimize information length for a given initial condition and the final the condition on beta and y. And that requires solving Euler-Lagrange equation for the two variable beta and y with the proper boundary condition. And from there, once you know what the functional form of beta t and yt's are, then we can find the functional form of dt and gt. All right. So I will just show you some equation. I consider the initial x mean value to be y0, which is larger than yf. So I'm considering the mean value decreasing in time. And I fixed the initial and final PDF width to be the same with the value beta 0. And after long calculation, which took me actually a long time, I found what the beta t is as a function of time, and similarly yt. All right. And then from there, I also found what how d and g should depend on time. I will just show you some sample example. Here, the mean x0 value at t equals 0 was chosen to be 5, 6, and final value 130. And I'm showing you the snapshot of the PDF, starting with the red one at t equals 0, and the final PDF, the shown in blue. And I'm showing you a few PDF in the intermediate state. And you can see that as a PDF moves, it gets broadened and then gets narrow again. All right. And we can systematically look at how the mean and the variance changes now by plotting the time trace of the mean value in red, here y, and the 1/, square root of the inverse temperature, which is standard deviation, in blue. So mean value obviously monotonically decreases. However, standard deviation now first increases and then decreases. This suggests that the PDF gets broader and then gets narrow. And we can also look at this evolution now using the phase portrait by plotting the standard deviation against the mean x value. And you start from here and you go to the left. So mean value obviously decreases while the standard deviation increases and decreases. And these two sets are obtained for particular inverse temperature beta 03. And I look at the other case where actually the inverse temperature is 10 times larger, which is to say I'm going to consider much narrow initial and final PDF. Again, the mean value decreases over time, as you can see here in red line. But now the standard deviation looks almost like constant. However, if you look at very carefully, there is a little oscillation. And this oscillation can be seen more clearly in the phase portrait. So you start from here and then goes through this mini circle. And in fact, I didn't know there was a name for such geodesic. I only realized that there is a name for such a solution. It's called the Poincare upper half plane model. It's called upper half plane because y-axis is the sigma, which is non-negative value. So the y negative axis does not exist. You have only phase space defined in the half plane. And the geodesic in this coordinate is almost like a circular, and you can do the coordinate transformation to get the equation in terms of y over square root t and sigma, and that is just a metric tensor for hyperbolic geometry. It's a plane, but there is also a disk version. And this hyperbolic geometry is very common in nature, and especially in beautiful painting, and it has negative temperature and negative curvature. And you can even make a career out of drawing this hyperbolic geometry if you are keen, if you are good at art. And these are the two examples of hyperbolic geometry. Okay, so now I'm going, so far I showed the case of the two different values of the initial and the final inverse temperature. And I try also all different values of inverse temperature. And I compare the total information length for the geodesic solution with the total information length for the non-geodesic solution. Here, non-geodesic solution that I consider is the solution evolving, keeping the same width, but the mean position changing at constant rate. This is an example that I could think of. And in this case, you can see that geodesic solution gives you the total information length, which is always smaller than what non-geodesic solution. And furthermore, in addition to giving you small total information length, I also show that the geodesic solution gives you the smaller total work that is involved in evolving initial to the final PDF, and also the total time that is required in reaching the equilibrium. And finally, I need to show how D and G should depend on time is quite interesting. The D is shown in red dashed line, and you can see some sort of oscillatory behavior. And similarly, the treatment term GT, starting from G0 increases, but in addition to increasing, there is oscillatory behavior. And this was very encouraging because when I was interested in the tumor, I happened to read some papers saying that when you want to kill tumor, it's always advantageous to apply periodic treatment rather than constant treatment. And to me, this geodesic solution is some treatment that is more friendly to your system, so it gives you less impact in your system. For instance, if you want to get the radiation in your body, it's good that you can kill a tumor, but however, it disturbs all your system in different way. So it's useful somehow to minimize the change that is required in your body in giving the treatment. And that is what I'm thinking. And to conclude, and I have shown that information length gives us total number of different statistical states that the system evolves through in time, and tau is the dynamical time scale of the information change. And I have discussed the linear nonlinear geometry due to linear and nonlinear force. And I show that L infinite shows the sensitive dependence on the initial condition for chaotic attractor like Lyapunov exponent. And I show an example where geodesic solution can be used for optimal control. And I didn't show in this talk, but I also look at simple quantum system to show the dual role of the PDF width in quantum system. And I have applied this PDF method to many different systems. It's like a fusion data or brainwave and atmospheric data or music data and etc. And what I'm keen on is to find the signature of geodesic in nature or the self-organization, which is my favorite topic in nature. And if you find the signature of self-organization, which is optimal for the survival of the living organism, you can also use the signature to design some intelligent machine. And I realized that you work on very interesting research topic, and I'm very keen on finding some collaboration on any area of your expertise. And thank you very much. And I will leave with here some references on information length.
So thank you, Prof. Kim, for this wonderful talk.
Thank you. And thank you for being so wonderful audience. It was great to talk to you during the talk. I wish we can do this every day.
So Igor, we already have a raised hand. Igor, please go ahead.
Yeah, so I wanted to ask about this measure L of the number of statistical states. In the case of, it wasn't in your talk, but maybe you have some ideas in case of conservative, strong conservative chaos, possibly in highly dimensional systems. Where, so if a highly dimensional Hamiltonian, for example, system is in a regime of strong chaos, and we start with some localized probability distribution, immediately after a few Lyapunov times, probability distribution fractally covers all the phase space. So will there be some explosion of this L in such a system, or what will happen?
I mean, that's something that I really want to explore through you. I know you work on very interesting topics in quantum and Hamiltonian system, especially some phase transition or something. And it looks like that, I mean, you are not really looking into this particular aspect. And I think you have all the machinery already that can be used to explore this concept. I mean, once you go into quantum mechanics, it's very interesting. I mean, I look at simple example of the Gaussian packet under constant force. And in quantum mechanics, you deal with the wave function, and you can look at the wave function in the coordinate space, the x space, or the momentum space. So how different information lengths you will get if you use the coordinates, the x space and the momentum space. And so, and this is something that I really want to look into detail, but I haven't had a chance yet, apart from looking at some simple Gaussian wave packet under constant force. And then I also look at the damped harmonic oscillator, where I found something interesting. But beyond that, I haven't had an opportunity to look any further. But if you have any idea, please feel free to email me, and I'm very happy to discuss further.
Thank you.
Okay, let's see if there are more questions from the audience. I think we had quite a bit during the talk itself, so I think people have exhausted their questions just during your talk. So since there are no more raised hands, let's all thank our speaker once again.
Thank you very much. Thank you.
Yeah, and with this, we will officially end